Let us discuss series of non-negative terms. Of these, the simplest is the geometric series. Okay, in the geometric series, we have a sum of some term x to the power k, and it's going to convert to 1 over 1 minus x if that x is less than 1, but positive, not negative, and it's going to diverge otherwise. Okay, the way we prove that, it's actually very easy, so let us mention it. We take the partial sums and we just need to write them down. Like this would be 1 plus x squared and so on, all the way to xn. And then we can just consider x times the partial sum, okay, which we can write down. This would be x plus x squared plus x cubed plus xn plus xn plus 1. Okay, now notice here we have a lot of repetition, right? So actually we will have cancellation if we subtract the first line from the second. Sorry, the second from the first. So this will be 1 minus x Sn equals 1 minus x to the n plus 1. Okay, so Sn is 1 minus x s plus 1 over 1 minus x. And here, when n tends to infinity, because x is less than 1, any number that is less than 1, as we raise it to a power, to something that goes to infinity, we get 0. So what we are going to get is 1 over 1 minus x. And the limit of the partial sums is, by definition, the sum of the series. Okay. Now, there is a theorem for non-negative terms that is due to Cauchy. Cauchy for non-negative series, okay? And here what we assume is that we have a monotonically decreasing sequence. Okay, and this actually happens quite often. So we have terms, a general term that decreases, but still it's non-negative. Okay, if we have that, then the series is going to converge if and only if the series sum of 2k a to k from k equals 0 to infinity, and this series is a1 plus 2a2 plus 4a4 plus 8a8 and so on, okay? So if and only if this funny series, let me rearrange this so that we have some space. If and only if this series converges. Okay, so what we are saying here is that the series is going to converge as long as this new series that is actually, if you think about it, it's quite thin because you are throwing away most of the terms of the original series, right? You are just keeping the powers of 2. So you are keeping just a few of them, giving them weights. Okay, and if you know that that one converges, then the original one will converge too. It's actually kind of funny if you think about it. All right, so how do we prove this? maybe funny is not the word, probably surprising is more it. How do we compare the sum of an and the sum of yeah 2k a2k? Let's call this, well, let's give it this. So this is n equal 1 to infinity, k equal 1 to infinity. So we are going to look at partial sums. Okay, we call Sn the sum of the original, the partial sum of the original series, and Tk, sorry, the partial sum of the second one. So 2a2 and so on plus 2k a2k. All right. And here now we need to compare. Okay, so what we are going to do, we are going to look at Sn, right, which is a1, a2, all the way to an, and just notice, okay, that we can make a rearrangement here. We can do like a1, a2 plus a3, a4 plus a5 plus a6 plus a7, and so on, okay? And always start with a power of 2, a2k plus, and so on, and then stop before the next power, 2k plus 1 minus 1. Okay, what we are doing here, we are making groups in the sequence. Now notice this arrow will apply as long as n is less than 2k. Okay, because here we have up to 2k terms, and here we are writing more terms. So what we have on the right is bigger than what we have on the left, for sure. Okay, but I wrote it in this way. It may sound a bit strange, but if you notice, I have grouped in powers of 2k. Okay, so I'm doing that because now I can estimate and say, well, you know what? So this is less or equal than a1 plus. Now in this group, a2, a3, because this is decreasing, the largest is a2. So I can estimate a3 by a2. Okay. Then in the next group, the largest is a4. Okay, but I can estimate every term by a4. So this is less or equal than writing 4 times a4. And so on. I can do this in every group, and I can have 2k times a2k. All right. If you count them, here what we have are actually 2k terms. But once I write it this way, the whole thing I did because once I write it in this way, this is the definition of tk. So this relates Sn with tk. Okay, the Sn is less or equal than the tk. But I can do it the other way around too. I can start with the Sn. Again, this is a1 plus a2 plus a3 all the way to an. And now I can just drop some things, okay, and say, well, this is bigger or equal than a1 plus a2 plus a3 plus a4 plus, and so on. And now keep a2k minus 1 plus 1 all the way to a2k. All right. Why do I do that? By definition, the sequence is going to be decreasing, so I have a1 plus a2, and now between a3 and a4, the smallest is a4. So I can estimate a3 and write twice a4, and so on. And then in the last of the parentheses I wrote, I'm going to have 2 to the k times the smallest, which is a to k. All right. But now, here notice what happens. This is not exactly what we had in the definition of, sorry, this is 2k minus 1. Okay. This is not exactly what I had in the definition of tk. This is the definition of 1/2 of tk. Okay, so this is bigger or equal. Notice here, this is bigger or equal than 1/2 of a1. So this is bigger or equal than 1/2 of a1 plus 2a2 plus 4a4 plus 2k a2k. So this is tk divided by 2. Okay, of course here, to be able to do the very first step, I need n to be a little larger than 2k. All right, but here we are saying just looking at the tail of the sequence. But now, what happens here? So we have Sn bigger or equal than tk over 2. So it doesn't really matter what case we are on. The first one we have Sn less or equal than tk. The second one we have Sn bigger or equal than tk over 2. Okay, but here, or if you want, we can say 2Sn bigger or equal than tk. Maybe it's a little more elegant. There we go. What we conclude from here is that either both or none are bounded. Okay, and we know that if a sequence is non-negative and bounded, it's convergent, and otherwise it's divergent. Okay, so that means either both or none, well, both convergent or both divergent. Okay. Now, one important consequence that we have been using for a while, the first one is that the series 1 over n to the power p, n equal 1 to infinity, converges if p is larger than 1 and diverges if p is less or equal than 1. This is the p series test. Okay, and here the way we show it is using Cauchy's theorem. Okay, so if we have p larger than 0, we are going to take the sum n equal 1 to infinity 2 to the k, and here I write a to k. Okay, but the a to k is 2k 1 over 2kp. Okay, but notice what happens. There is a simplification I can do, right? So I'm going to get 1 over 2 to the p minus 1 k. And now this is a geometric series. Okay, and it converges if p minus 1 is positive and diverges if p minus 1 is non-positive. Okay, if p is larger than 1, I have actually, I can write it like this, 1 over 2 p minus 1, all of it to the power k. The 1 divided by 2 to the power p minus 1 is going to be smaller than 1 if p minus 1 is positive, or the other way around. Okay, if p is equal to 1, then I have I'm adding 1 every time, infinitely many times, so that won't work. And now I realize I was writing n as the index, but I should have been writing k. So this proves it. But we can make it even apply this to more complicated series, okay? For instance, we can have 1 over n logarithm of n to the power p. Okay, and now we are going to take from 2 to infinity, because what happens when n equals 1? That the logarithm is 0. So I will be dividing by 0, so no chance of convergence. Okay. But here we have a similar result. We have that this converges if p is bigger than 1, and diverges if p is lesser or equal than 1. Okay, and the proof again is using Cauchy. K, well, doesn't matter. 2 to the k, let's write it first in the general format, then we write the particular case. So this is 2k, 1 divided by 2k, the logarithm of 2k to the power p. Okay, and here we are going to take k from 2 to infinity. I said it doesn't matter because a few terms, as long as we don't divide by 0 or anything strange, a few terms more or less don't make don't make a difference in the convergence. They may change slightly the final result of the sum, but that's not what we are looking for. We are just deciding convergence or divergence. Now here the 2 to the k cancels out, and we have sum from k equal 2 to infinity, and here we have 1 divided by properties of logarithms, k log 2 to the power p, k equal 2 to infinity. So this is 1 divided by k to the p log 2 to the power p. And this is actually a constant, the logarithm. I'm using the natural logarithm. Okay. And this is k to the p. And we just saw this by p series converges if p is bigger than 1, diverges if p is less or equal than 1. Okay, so it's a very similar computation. The logarithm there sounds kind of threatening, but actually with this result from Cauchy is very easy. And in the homework, there is a further twist. So what we are going to see in the homework is decide the convergence of 1 divided by n log n times the logarithm of n to the power p. Converges or diverges.